So this week we are working on Chapter 5, titled The Beast of Bias. So on the first day of class, we looked at sampling bias. For instance, when participants with certain characteristics are more likely to be selected. So such bias can corrupt our external validity of our findings. For instance, it probably wouldn't be reasonable to hand out a survey only the internet, because this method you wouldn't reach everyone. What about those people who are not computer savvy, or those people who do not have access to the internet? Recruitment location can also introduce survey bias. So for instance, depending on the locations that you use to collect your data. So for instance, if you're wanting to post recruitment flyers, what if you're only doing it in a women's locker room, in a sports bar, in the lobby of a technology company, just certain select places where only certain groups of people would be? You're not opening it up to the entire public, so your sample would be diverse. This would lend itself to your study being biased. So we've looked at sampling bias. Now we're going to look at other ways that our data can be biased. So this week we're looking at assumptions. So parametric statistical tests have assumptions. So I'm sure you're wondering, okay, so what is a parametric test? Throughout this semester, starting next chapter, I think it's starting the next chapter, we're going to look at statistical tests are going to fall into two different categories. They're either going to be parametric or non-parametric. Parametric tests have certain assumptions that you must meet. So think of it kind of like a checklist where you have to meet all of these different criteria in order to conduct a specific statistical test. So for instance, each week as we look at different tests, I'm going to list, if it is a parametric test that we're looking at, for instance, t-test is an example of a parametric test. I will discuss that week what assumptions you have to meet in order to complete a t-test. If your data does not meet every last one of that criteria, you should not complete a t-test. So again, we want to make sure that our data meets certain assumptions before parametric tests can be used. And you always want to check to make sure that your data don't fail these assumptions. And it's going to be different if those of you who will actually, who may actually potentially collect data one day, because real data in the real world can be quite messy. In our textbook, usually our data are fine, they meet the exceptions, but in the real world, it's not uncommon for your data to not meet one of these assumptions. And when that happens, there are certain things that you can do. For instance, you might end up using a non-parametric test. So again, I'm going to, as we move into the semester, we are going to know which tests are parametric and which tests are not parametric. So talking about assumptions of parametric data. Each parametric, so there are pretty much general assumptions of parametric data. A lot of the parametric tests follow the similar criteria. However, some of them have more specific criteria for their particular test. But generally, parametric tests are based on normal distributions. Every parametric test that you will complete, you have to make sure that your data are normal. If your data are not normal, if it does not follow a normal distribution, you should not use a parametric test. So make sure that your data are normally distributed. Also, we want to look at the homogeneity of variance. So basically, we want to see if the variance is the same. And this falls under the category if you have more than one group of data. More than one group in your data set. So for instance, if you have a data set where you're looking at males and females, you want to compare the responses of males and females, well then you're going to be comparing two groups. And so before you conduct that test, you want to make sure that the variance of both groups are similar or the same. So the variances should be equal throughout the data, and the groups should have equal variance. There's times where you might be comparing more than two groups, for instance 3 groups. Again, you want to make sure that you meet that criteria of homogeneity of variance. Another basic assumption of parametric data would be your dependent variable. Okay, your dependent variable, remember that's that outcome variable, that should be interval or ratio variable. And finally, independence. So for independent designs, the data from different subjects should be independent. So basically, if you have handed out a survey, you have a sample of 30 people, each of those 30 people should have completed that survey on their own, not with anyone else. They should have completed it independently, so the responses that you have received from each and every person will be completely different from one another. Also, another instance where your data would be independent, for repeated designs, the time variable will be dependent. And repeated designs, that falls under the category of if you have a pre-test and a post-test. For instance, if you are part of, maybe I am looking at a new math program that's going to be implemented in this school, and I want to see what effect this new math program has on their math achievement scores. So I'm going to compare two groups. I'm going to look at one group will be my control group. They will not have this new math program. They're going to be taught with the same math strategies that have always been used. My other group will use the new math program. This is going to be my experimental group. Okay? So I'm going to look at two different times here. I'm going to give them a pre-test to see how well what their math achievement looks like, and then I'm going to give them a post-test, again after this math program has been implemented. For example, maybe 6-9 weeks, or maybe a whole academic year. It just depends. So repeated designs where you are collecting data multiple times, that time variable will be dependent. Okay? And then your subjects, of course, should be independent of each other. So I have my control group and my experimental group. Those subjects are going to stay in those same groups. They're not going to move around. They're going to stay in those same groups. So one of the ways that you can test for normality is by using a PP plot. So this is called a probability plot. So basically, when you complete this PP plot, if your data, basically your data are plotted along this line, and it's going to be plotted this way, and how closely it falls along that line, that linear line, shows how normal your data are. So for instance, if you're looking at day 2 right here and day 3, they are not, these plots are not falling on the line. Again, they are not falling on the line. So day 2 and day 3 are not normal, but day 1 is. And if you look at that normal curve, you can clearly see, look at the difference here. Yes, that is pretty much a normal distribution. whereas day 2 and day 3 are both positively skewed. So one way that we're going to test the skewness and kurtosis of our data is we're going to interpret it using z-scores. And so I want you to be very careful, because this is an example here of descriptive statistics that here's a table that will pull up whenever you click on calculating those descriptive statistics. So now please do not make the mistake of saying, oh, skewness negative 0.004. That is my answer. No, that is not the answer. You're going to have to plug this into a formula. So this is actually found on page This is actually found on page 184. I'm just pulling these formulas and this table from page 184. So for your kurtosis, the formula is your skewness I'm sorry, it should be, I have a typo here, sorry about that. So for your kurtosis, it should actually be K minus 0. So it would be your kurtosis statistic here minus 0 divided by the standard error of kurtosis. So that's why it's negative 0.410 divided by 0.172. And that would give me a kurtosis z-score of negative 2.38. So once you get this number here, now you have to determine if it is significant or not. And these are your indicators. So we have our different p-values. You choose what p-value you would like to use. I'm going to choose 0.05. So if my z-score is greater than 1.95, that means that it's significant. Okay? So if it's significant, that means that there is a problem with kurtosis. If it is significant, there is a problem with kurtosis. But in this case, it is less than 1.95, so I do not have any problems with kurtosis for day 1. I'm only looking at day 1 here. Now, let's look at my skewness. Skewness formula is very similar, so I'm going to use my skewness statistic minus 0 divided by standard error of skewness. So that's where I have negative 0.004 divided by 0.086, which will give me 0.047. So again, I'm going to use this to help me interpret it. Again, I'm sticking to 0.05 as my p-value. Whatever p-value you decide to use, you have to stick with it. So for instance, I couldn't say, oh, I'm going to use 0.05 for kurtosis and then I'm going to use 0.001 for skewness. No, it needs to be consistent. So I've just decided that I'm going to use 0.05 for day 1. And so I have my skewness z-score would be 0.047, and again, it is not greater than 1.95. So based on these indicators, using my 0.05 p-value, skewness and kurtosis are non-significant, which indicates there are no problem with skewness and kurtosis. What if I'm looking at day 2? So again, I'm using the same method. My kurtosis z-score is 2.75. Now look, Now this one is actually greater, so that means it is significant. Kurtosis is significant, so that means that there is a problem with kurtosis here. Let's see skewness. Yes, skewness is way greater as well. So day 2, there's a problem with skewness and kurtosis. And let's look at day 3. So again, same procedure. It looks like there is 1.69 is less than 1.95. So kurtosis, it's non-significant, which indicates there is not a problem with kurtosis. But skewness, if I look at my skewness, it is greater than 1.95. So in this case, there are no problems with kurtosis, but there are problems with skewness for day 3. So significant tests of skew and kurtosis should not be used in large samples because they are likely to be significant even when skew and kurtosis are not too different from normal. So your book indicates large sample size is greater than 30. When I think of large sample size, I'm thinking of, in the thousands, close to 1,000 or greater, I would consider a large sample size, because the larger that sample size is, that's when those significant tests, they're going to be significant regardless, just because your samples are just so large. So another way that we can determine the normality of our data is by using the KS test. Let's see, the Kolmogorov-Smirnov test. I know I butchered that, but I've been practicing. I tried the best I could, but let's just say KS test. So basically, this test is going to be used with continuous variables. It must be used with continuous variables. And it can be used to test whether the distribution of the data differs significantly from a normal distribution. So again, using numbers, so we had our PP plot that we looked at. We can see if our data were normal. We can use our skewness and kurtosis statistics, because again, if there are no problems with skewness and kurtosis, that would tell us that our data are normal. We can also use the KS test. Okay? So the interpretation of a KS test will depend on the p-value and the sample size. So let's look at this table here. So basically, if we look at any sample size, if that p-value is going to be less than 0.05, any sample size, the population is unlikely to be normally distributed. If it's not going to be normal, use a non-parametric test. If you have a large sample size, greater than 30, and your p-value is greater than 0.05, that means that it is not significant and your population is likely to be normally distributed. It's not significantly different from a normal distribution. That's what we want. We want it to be non-significant. Okay? So in this case, we can use a parametric test. Okay? How large does the sample have to be? There's no firm answer, but a rule of thumb of 30 or more. And for small sample size would be less than 30. If you had a small sample size and your significance ends up being greater than 0.05, you might think, oh, good, it's non-significant because it's greater than 0.05. You might be tempted to say that, oh, my population is normally distributed. Please do not do that, because small sample sizes do not provide enough data. So if you have a sample size of 15, for instance, and you are completing your KS test, oh, my significance test is greater than 0.05, my data must be normal. Do not make that assumption, okay? If you have small sample sizes, there are certain non-parametric tests that you can use. So, for your KS test, you definitely want to select a non-parametric test when the outcome is an ordinal variable. For instance, if you have a survey using a 5-point scale, and if that particular outcome uses that 5-point scale, it's ordinal, so stick to a parametric test. Now, when in doubt, some people choose a parametric test because they aren't sure that the normality assumption is violated. They're hoping that it's not. While others choose a non-parametric test because they aren't sure their normality assumption is met. I would always err on the side of caution. If I do not have enough information about the normality of the data, I would choose a non-parametric test. Now, another test that we can use to assess the variance homogeneity is the Levene's test. Now again, this is for multiple groups. This is for 2 or more samples. We would assess the variance homogeneity. So an assumption, again, this would be like your t-test where you're looking at 2 groups, or your ANOVA where you're looking at 3 groups. So again, this would be an assumption for parametric tests like your t-test or your ANOVA, which we will talk more about in the semester, so don't freak out if you have no clue what a t-test or an ANOVA test is. That will come, I promise you. So basically, when you're looking at your output, if your significance is less than 0.05, your variances are significantly different, and the parametric test cannot be used. Again, we want our hopes, if you want your variances to be similar, well then you don't want your findings to be significant. You want them to be non-significant. Non-significant is telling me that they are the same, they are similar. So if your significance is less than 0.05, then your variances would be significantly different, and that would mean that you would have to use a non-parametric test. So these are the major components of the major topics from Chapter 5. Chapter 5 is a heavy chapter, and so I hope you didn't feel too overwhelmed. But if you did feel overwhelmed in Chapter 5, it will be okay, I promise. I'm only going to, it's a lot to take in, so I'm only focusing on those topics that I feel are most important for Chapter 5. This lecture was the content portion of this chapter. Notice the beginning of the lecture said part 1. There's actually a part 2 that's going to be coming shortly, and that will focus on using SPSS. Thank you.